Take two, round two. Well, we got Taylor this time.
Hello, Tom.
Hey, buddy, how you doing?
I'm not too good, mate. Yourself?
Oh, well, I'm amazing.
Good. When the bloke at work said the symptoms of the virus who I was working with yesterday.
You what?
One of the blokes I was working with yesterday had the virus.
They probably got it off you. You were ill, weren't you?
You better be self-isolating then.
I was ill, lad. I was ill yesterday. I was ill over the week.
Probably give it to him.
They're saying that Regan.
Right, yeah, I know. Okay, so we're doing learning outcome 4, examine how differential and integral calculus can be used to solve engineering problems. I don't know how many of you will have done any calculus before, but it consists of 2 interrelated topics. First is differential calculus. So that's around problems involved with finding the slope or the gradient of a function, determining rates of change, and solving problems related to displacement, speed, acceleration are just some of the things involved with that in engineering. And then we have what is the mathematical opposite of differential calculus, that's integral calculus. And it's about problems around finding the area beneath and between functions and finding the volume of complex solids, solving of differential equations. So over the remaining weeks of this module, we'll be looking at that. All right.
Yeah.
So moving on to second and third pages of the handout. On the second page, there's a little drill there that's asking you some questions. I want you to have a look at that and have a look at the remaining drill on the next page based around some stuff that we've already covered. All right, so 5 minutes on that and then we'll go through it. Okay.
All right.
Can you guys actually hear me?
I can hear you.
No.
Oh, cool.
Splendid.
Splendid.
Yeah. What we can do is keep the 3, bring the x up and change the sign of the index. Yeah. Where that comes from is we could write this as 3x to the 0 over x to the 3. When we divide with indices, we take them away, so it becomes 3x to the 0 minus 3, which is 3x to the minus 3. We need to be able to do that to do the differentiation. If we've got something in fractional form, we need to be able to bring the power of x up to the top, and that's how we do it. Just move up, change the sign. Okay?
Yeah.
Can anyone remember how we can write x, square root of x in indices form? Is that x to the power of something?
X to the power of 1 over.
You're nearly there.
1 over x.
Sorry. X to the power of a half.
That was close.
Yep. And this one, the 3, the number outside the root goes in the denominator. So this is x to the 2 for the squared over 3. That's how you do that. So if you think about it, this number always goes as the denominator of the fraction. This one is the numerator. Yeah?
Yeah.
Okay with that, everyone? Everyone all right?
Yeah, it wasn't too hard, was it?
So when we want to differentiate functions with those types of parts to them, we have to write them. We're going to have to change them into this indices form. Yeah. We're doing for time 22 minutes gone.
Just like
Right.
that. We can blame Connor in the time.
You all got that down, yeah?
Yeah.
Good. Right. So, functional notation. I want to talk to you about now. If we got equations such as y is equal to 3x squared plus 2x minus 5, that is a function of x. So y is a function of x. It depends on the value of x according to that function. Okay, we can write that is this in this form here. Y is equal to f of x. Yeah, it's kind of functional notation, doing it this way. All right, and then we can denote the value of the function of x when x is equal to 0. So if we say x is equal to 0, we denote that as f at 0. Yeah. If we had the value of f of x when x is equal to 2, we'd put f of 2, and so on. All right. So if we're evaluating that function at f is equal to 0, all you do is everywhere where there's an x in there, we put 0. We evaluate that. So that function at 0 is equal to minus 5. Yeah. So that means that y is minus 5 when x is 0. If we set x to 2, function f of 2, y is equal to 11, and so on. Okay? So that's functional notation.
Nice.
So the gradient of a curve. So if we've got a function that is a curve, like that shown on the screen, and the gradient of this, if we put a tangent at a point P anywhere on the graph, okay, then the gradient of that tangent is the gradient of the curve at point P, or the slope. All right. So we could find that gradient by gradient is equal to the change in y, which is designated by that lowercase delta times y, divided by the change in x, or delta x. All right. So the gradient of any graph, if we take a curve and we put a tangent at a point, we find the gradient of that slope by calculating the change in y divided by the change in x. All understand that so far?
Yeah, baby.
Yeah. Good. Right. Now, later on, you will see when we start doing the calculus that the gradient of a tangent to the curve f of x is equal to x squared, just x squared is equal to 2x. And hence the slope of f of x when x is equal to 1 is f dash of x. So that means the first differential. Don't worry too much about that at the moment, but you'll find that the slope of the graph is equal to 2x, and where x is 1, the slope is equal to 2. But if we look at how chord lines can develop towards being the tangent, so if we take the 2 points A and B, they're not very close together, and the gradient of that chord, or the slope of this green chord, is change in y, which is 9 up here, minus 1 at the bottom, 4. If we move a bit closer to the point C, the gradient of that chord is 4 minus 1 over 1 is equal to 3. And if you can just see that yellow one in there, we move to a point a little bit closer still, D, then the gradient of that chord is 2.25 over minus 1 over 1, 1.25. So as we move closer and closer towards this point A, the slope of the chord gets closer and closer to the slope of that red line there, which is the gradient at point A. Yeah.
Where'd you get the 2.25?
Yeah.
Where do we get that from?
Oh, hang on. That's 1.5, isn't it?
Yeah.
So that's 1.5 minus 1. It should be this a half there.
It does say.
Typo.
Oh.
This bit should be 1.5 minus 1 over, and the change in x is 0.5.
But then the purple line starts at 2 as well.
Yeah. The point I'm trying to get to, I'll need to put that right, okay? But the point I'm trying to get to as delta x gets smaller and smaller, the gradient of the chord gets nearer and nearer to the value of the red line slope.
Yeah.
All right? Yeah. So from that, I don't want you to get too hung up on this detail, really, because what I want you to be able to do is do the calculus, not understand the theory behind it too much. Okay? So,
Who's dog?
differential coefficient. When the value of delta x tends towards 0, so as it tends towards 0, the gradient of the tangent is found, and this is called finding the differential coefficient. So this is what we really want to be able to do. Yeah. You all got that table of standard derivatives that I sent to you?
Oh,
Yes.
yeah, baby.
Yeah,
Yeah.
because you're going to need that all the time. Yeah.
It's a beauty.
All right.
I do have one.
Then print it
So
out, but
yeah. So as far as I'm aware, you won't need any more than that. If you do, I'll be giving them to you another way, and you can add them to that list. Be careful, there's two sides to it. At the moment, we're working on the side that has the table of standard derivatives. Yeah.
yes, Gav.
So if we've got a function y is equal to f of x, the differential coefficient is written like this: dy over dx, and that's pronounced dy by dx. Yeah.
Mhm.
So when using functional notation, if we've got a function f of x, we can also write the differential coefficient as f with a single dash of x. So we can either write dy by dx, or we can write f dash of x. Okay?
Yeah, baby.
So those two way expressions are equal to each other. In some situations, we'll be using dy by dx. In other situations, we'll be using the notation f dash of x. All right? Yeah.
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 Nice for you to join us, Regan.
Where is he?
Is he in it?
Regan's iPhone. Nice.
Toy.
Hope.
Hiya, Regan. I hate to tell you this, but in about 7, 8, 9 minutes, this room's going to run out of time, and you're going to have to get in again.
Oh, God.
The college has applied to have Zoom of lifted the 40-minute limit for educational institutions, so they're applied for that. That's just going through the check-in process now. So hopefully, the time Easter is over, because you're off the next 2 weeks.
Oh, we are?
Hopefully, this 40-minute
Are
limit
we?
will be lifted. Yeah, 2 weeks. I'm on a holiday for 2 weeks at Easter,
My
so
boss don't know that.
Wait, where are you going? There's not much you can
I'm
do.
not going anywhere. But I'm
Oh.
having a break from work. All right.
Nice. You enjoy
Okay.
it,
So
mate.
this, at the moment, I want to focus on the top part of this table of standard integrals, and that's on the screen now. Yeah. So if we have a function that is I times x to the n, so any constant times x to the power of n, what the right hand side is saying is the derivative of that is I. We keep the I. Listen, guys, keep the a, we multiply by n, and then we put x and we take 1 off the power. All right, and we'll be doing some like that. In fact, we'll be doing some basic ones like all of these, hopefully this morning. If we have a function that is e times a to the x, we bring the a out and we keep e to the ax. E to the power of x is a very special function because its derivative is the same as the function itself. And then ln x is simply 1 over x, the derivative is. Sine ax is a, cos ax is minus sine ax. So we use that table to determine what the derivatives of basic functions are. All right?
Gotcha.
Yep. So let's have a look what's on the next page. I think the first example's on the next page. I'm just going to go one more page forward and see what's on that. And let's see if we can get to try these ones before we turn off and start a new meeting. Right. So these examples. Find the differential coefficient of y is equal to 12x to the 3.
So could we say that 12n, oh wait, no. Could you use the second one down in the table?
We've got 12
Oh wait, no, it's the first one.
x to the 3. Yeah.
Yeah.
So we're in I x to the n as the type of function that we've got. Yeah. So what we do is we bring the 3 down in front, multiply it by the 12, and then take 1 off the index. So this is dy by dx. Yeah, and that's equal to 3 12s are 36 x squared. Yeah. So the first differential of 12x to the power of 3 is 36x squared. Okay.
Gotcha.
So that's A.
Come on, Dabo 2.
Show him about
B.
12.
So we've got 12 over x cubed. Can you see anything like that in the table?
No.
But how else could we write it so that you can see something like it in the table?
You can times it by x cubed.
Not quite. But we can bring the x up and make the index negative. Yep. Now it looks like a times x to the n. All follow that? So we can now go with changed this function into this form. So we've moved the x to the power 3 up to the top into the numerator and made the index, or changed the sign of the index. Yeah.
Gotcha.
So now we can do the differentiation. We can take -3 times the 12 times x to the power of, and that's -3 take away 1, so it's -4. That equals -36 x to the -4, which could also be written as -36 over x to the 4.
I see.
Okay.
Do you want to finish it off as a fraction or the
Um,
top one?
Either form, the top one would be fine.
Gotcha.
Okay.
Very smooth.
All right.
Right. Problem 2.
We're getting close to running out of time now.
We're 2.5 minutes, like a ticking bomb.
Okay, I think I'm going to stop that there, and we'll move on to a new room, because I don't want to lose the chance to save the recording. All right. So I will open a new meeting and see you in a minute.
Later.
Hi, Dom.
Bye.